Autonomous agents promise to scale back-end operations. You deploy them to handle complex, multi-step workflows. But at the end of the month, you look at your API bill and see an inexplicably massive spike in costs. When a system burns through tokens this rapidly, the culprit is rarely a single poorly written prompt. What you are looking at is a systemic architectural failure. Back-end components become disjointed, forcing the model to endlessly reread the exact FAME instructions. It is a structural paradox. The mechanisms we build for power, like dynamic tooling and background scheduling, sabotage native API cost-saving protocols. To reclaim control over these API costs, we have to abandon basic prompt optimization. We must treat context management as a rigorous, full-stack engineering problem. We will execute a strict 7-point diagnostic audit across this agentic workspace. The output of this audit is a strictly sorted cost-impact matrix. We categorize every issue by finding its severity, red, amber, or green, the hard evidence behind it, and the cost impact. Our operational boundary is strict. We make 0 code changes, only measuring the environment to populate these rows. Applying this rigid framework forces the system architect to actively hunt for the hidden configuration errors that silently kill prompt caching. Building this evidence-based matrix is the only empirical method to locate pipeline leaks and reclaim the agent's context budget. Step 1 audits static context. This is the baseline memory load, all the files and instructions loaded into memory before the agent takes a single action. This represents a standard 200K context window. We calculate the baseline footprint by measuring global project instructions, parent directories, and user-level imports. If a single instruction file, like a CLAUDE.md, exceeds 5 to 10,000 tokens, it permanently displaces usable working memory. This static weight creates severe performance drag during the deployment of subagents. A common configuration error occurs when a newly spawned subagent automatically inherits the main session's model and its massive front matter instructions. Subagents require a narrow, specialized scope. Inheriting the global context overrides that requirement entirely. Passing massive global contexts into narrow-scoped subagents guarantees redundant processing and continuous baseline token waste on every request. Static files are only one vector. The second step of the audit examines time-based context management. Specifically, we must evaluate prompt cache TTL, or time to live. This graph maps cache TTL, how long the model holds context memory to reduce costs. Now we introduce scheduled cron jobs. A critical failure happens if a cron job's interval exceeds the cache limit. The cached context drops to 0 just before the job executes. The system misses the cache. You pay the maximum cache creation token tax on every single execution. Step 3 targets the second dynamic cache killer, mid-session model switching. Automated architectures often switch models dynamically based on the specific effort level of a given task. Altering the model instantly flushes the accumulated context cache. This forces a complete rebuild of the working memory from scratch on the very next turn. Misaligned cron schedules and dynamic model auto-switching negate the economic benefits of caching architectures. Step 4 investigates external network routing, specifically checking for API gateways or proxy variables. This map compares a direct API connection path against a routed connection via a proxy gateway. On a direct connection, the system utilizes a tool deferral flag to avoid redundant processing. But on the routed path, the proxy gateway strips that deferral metadata during transit. Dropping this metadata forces the model to reprocess identical, heavy MCP tool definitions redundantly on every interaction. Warning tone. This metadata loss happens entirely silently. The system throws no terminal errors to warn you. You must check the total number of exposed tools on the server to understand the exact weight of this redundant processing. Routing through an unverified proxy can instantly multiply operational costs by silently neutralizing tool deferral. Step 5 shifts focus from the network pipeline back to the local execution environment, specifically examining pre-tool use hooks. Failing to rewrite noisy commands forces raw, unfiltered logs verbatim into the context window. This unmanaged garbage acts as a permanent, endlessly reprocessed tax. Step 6 transitions from theoretical architecture to empirical verification by examining the raw session JSON logs. This line chart tracks usage data for every assistant turn, mapping cache read tokens directly against cache creation tokens to calculate their exact ratio. Then it morphs into a bar chart comparing context payload size on the first and final turns. This final metric explicitly reveals the rate of compounding context bloat accumulating throughout the session. True system efficiency is never guessed. It is mathematically verified by analyzing the cache read ratio within the JSON logs. Step 7 returns us to the completed audit matrix. Populated with log data, it dynamically sorts by cost, pushing red severity items to the top. We isolate specific system components by targeting the single most expensive evidence point. Your ultimate imperative as a system architect is to identify and execute the single highest leverage architectural change based on the findings of this matrix. Fixing one critical systemic leak, like bypassing a proxy or correcting a cron interval, instantly stabilizes costs. Context is a strict computational budget that must be systematically measured, verified, and locked down.